Okay, welcome back everyone. In this video, we're going to start looking at different types of forces that we find when solving Newton's laws problems. And so what we're trying to get out of today's session is to look at these different types of forces, okay, including static and kinetic friction. And how do we use Newton's second law to solve problems with one or more objects in a system? And we're going to start by looking at the normal force. So the normal force is the force that keeps one object from invading another object. And when we say that, we're really not talking about a war, we're talking about physically how is it that one object doesn't pass through another. So for example, our weight is the force of attraction of our body by the center of the earth, but we don't fall all the way through the earth. And as a matter of fact, it's the normal force that keeps us up. Okay, so we would draw this. Here's the normal force on a flat surface. Okay, so here's an object, and we would draw the force of gravity going downwards. Sorry, that got cut off a little bit, so we're just going to label that as mg, as the force of gravity is equal to mg. So more about that later. And then we have a normal force, okay? Sometimes you'll see the normal force written with a capital N, and other times you'll see it written with an F subscript N, okay? And in this case, if an object is just resting on a horizontal surface, then the normal force is equal to mg. Okay. Now, another thing that's important to point out is that we typically want to draw these forces acting at the point of application. And so the normal force, if I redraw this box, normal force will act where the table is pushing up on the box, but the force of gravity actually acts at the physical center of the object. So that's something very important to keep in mind. And then if we apply F net is equal to ma, if a is 0, then we have F normal minus mg is equal to 0. And what we're doing is we're applying the fact that the normal force is in the positive direction, which we've just established here, and mg is in the negative direction. Therefore, the magnitude of the normal force is equal to mg. Now, is it always true that the normal force is equal to mg? Absolutely not. Okay, for example, if we have a ramp, okay, the normal force, well, first of all, gravity will be going down, and the normal force will be going up at an angle, which means that it's more convenient to say that we have a perpendicular and parallel direction for our forces. And it's convenient to split gravity up into a component that's parallel to the incline, mg sine theta, which also could be done this way. There's theta. And also mg cosine theta. So most of the time, this normal force is equal to the component of the weight perpendicular to the surface. So in this case, Fn is equal to mg cosine theta. It's not always true, but it is in this case. Okay? All right. Now, what acceleration would we have in this situation? So now we need to think about, okay, what is going on with all of our different forces? Well, the sum of the forces will be equal to mass times acceleration. And if we think about this, the block will be accelerating down the incline this way. So by the way, this is our angle theta here, in case that was not clear. So the block will be accelerating down the incline like so. And so the only force that we have in the parallel direction would be mg sine theta. So we've decomposed mg into its components, and so mg sine theta is equal to ma. And this tells us that A is equal to G sine theta. Now this is something that we should kind of do a real life check on. So for example, if the angle was 0, right? If theta was 0, A would be 0 because it would be sitting on a flat table. And also, if theta was equal to 90 degrees, A would be equal to G. It would be falling straight down. So we always want to sort of apply some thinking about this. Okay, so what could we do to keep this block from accelerating? Well, there's a couple of different things. One is to apply a tension in the backwards direction. And so what this would do is if T was equal to mg sine theta, then the net force would actually be 0. And therefore we would have no acceleration. Okay, so we're going to move on to tension and talk about that for a little bit. Okay, so tension is a pulling force that usually exists in a rope, a string, or a cable. And it really comes from the molecular level. So a rope, a string, or a cable resists being pulled apart because the individual molecules are chemically attracted to their neighbors. So there's a chemical bond between atoms or molecules. So one thing that we could look at is the concept of how tension is used in 2 dimensions. Okay? And so the horizontal and vertical components of the tension have to be equal to 0 if the system is not accelerating. So another way of saying that is that if we analyze the forces at this junction, so that's this point right here, we have 3 tensions, T1, T2, and T3. Whereas for the box, the 15 kilogram object, we have T3 and mg. Okay, now if it's not accelerating, we can write immediately that T3 is equal to mg. Okay, but we can also write that the sum of the x forces is equal to 0, and also that the sum of the y forces is equal to 0. And I apologize, I got cut off a little bit, but maybe if I write it here, it'll make you feel better. Okay, so this is the conditions of equilibrium. Namely, that the net force is 0 in the x and y direction. And then what we could do is we could go through and solve and say something like, looking at this juncture right here, T1 has 2 components given by a 45-degree angle, and T2 has 2 components given by a 30-degree angle. And if the sum of the forces in the x direction are equal to 0, we could write that as T1 cosine 45 minus T2 cosine 30 is equal to 0. And we're just going to say that upwards is positive and to the right is positive. We could also say that the sum of the forces in the y direction are equal to 0. So that would give us T1 sine 45 plus T2 sine 30 minus T3, which we know is equal to mg, is equal to 0. And this would give us a system where T1 and T2 are the variables and we have 2 unknowns. Okay, so another important application of tension are the infamous elevator problems. And so if an elevator is accelerating upwards, what would the forces look like? Well, we would have tension going upwards, but tension would have to be much greater than mg because the acceleration would be positive. So again, upwards would be the positive direction. Or in other words, t minus mg would have to be greater than 0. What if the elevator is moving at a constant velocity in between floors? Then what would things look like? Well, for this, we would have to have T is equal to mg, so that the sum of the forces, T minus mg, would be 0. So A is 0 and V is constant. And then what if the elevator is slowing as it comes to the top floor? Well, in that case, if you think about it, which way would its acceleration have to be? Yeah, the acceleration would have to be down, which means that the force of gravity would have to be greater than tension. So mg would have to be greater than T, so that mg minus T is greater than 0, but in the downwards direction. And as a matter of fact, we would write mg minus T is equal to ma, assuming that downwards is positive for acceleration. And then finally, what if the elevator breaks? The elevator cable breaks. That would be a bad day. Well, in that case, we only have mg, and so F net would be equal to ma. So you have mg is equal to ma, and hopefully this makes sense. It would just have an acceleration of 9.8. It would be falling in free fall if there's no other forces except for gravity. Okay. So now what about pulleys? Well, pulleys are magic. And what magic pulleys do is they just bend the coordinate system. So what does that mean? It means that if I have an x coordinate running this way, then it just bends and x goes sort of downwards for m2. And so you might notice that my font just changed color suddenly, so I've actually switched to a slightly different version of this presentation. But really what happens is that pulleys allow us to continue a straight line coordinate system, and if we were to draw the forces on each of these objects, M1 would have a tension, it would have a normal force on N1, and it would have M1 times G. Notice that Fn1 and M1G would probably cancel out so that the net force would just be its tension. And then for M2, it would have M2G and tension, and those would not necessarily cancel out because M1 would probably accelerate to the right and M2 would probably accelerate down. So all of these pulley problems should be started from a force diagram. And so this is going to be an angle theta here that we'll use. And we're going to write Newton's second law separately for each object in each direction. So there will be 3 equations in this case, because we'll need 2 equations for M1 and 1 equation for M2. And here you have them. Okay, so here are the forces. Okay, so M2G is going down, tension going up, and then we have tension, the normal force, and M1G for M1. So what we would do is, first of all, we would take M1 and we would take the force of gravity on it and say that this would also be our angle theta. And so therefore, if we guess that it accelerates up the ramp, then F net parallel would be equal to M1A. And so T minus M1G sine theta is equal to M1A. And M2G minus tension is equal to M2A. Again, we would assume that this accelerates down. So we would just combine those by adding them. And that would allow us to solve for the acceleration. Okay. Now the tension we can get by looking at one block or the other. So we have the same setup. Again, this is a force going downwards. So the sum of the forces on M2 is equal to M2 times A. So M2G minus tension is equal to M2A. And we do the same thing for F1. And we would be able to plug in our acceleration that we found in the previous slide and solve that for the tension. Okay, so we'll kind of wrap up our discussion of tension by considering the Atwood machine. Now the Atwood machine is a neat device for measuring gravity. So if we know M1 and M2, then we can kind of set them so that the acceleration can be measured. And if they're pretty close to the same value, then we're going to get close to zero acceleration. And we can measure g from this. So what do we mean by that? So here's the forces on each of them. And if we assume that M1 is a little bit bigger than M2, then we could write the sum of the forces is equal to MA. And we get the expression M2G minus M1G is equal to M1 plus M2 times A. So how do we get that? Well, for M1, we would assume that it accelerates down. Okay? And actually, I think for this one, we'll assume that this accelerates up. So T minus M1G is equal to M1A. And for M2, that will have to accelerate downwards. So we'll have to have M2G minus T equals M2A. And then if you take this system and you add them together, that's going to take you down to this one here. M2G minus M1G equals M1 plus M2 times A. And then the acceleration would simply be G M2 minus M1 over M2 plus M1. And we could note from this that when M1 equals M2, the acceleration is 0, right? Look at that numerator. And also, when M1 or M2 equals 0, the acceleration is g, 9.8. Okay? So you always want to kind of check these expressions to see that it makes sense in real life. Okay, so next time we'll do a little bit more with ramp problems, and then we'll start talking about friction.